It's a fantastic data set. Because and it took a long time for them to set up the experiment, to set up the apparatus in this way. You know, it's a real learning curve. They have to make sure there are no leaks.
And they check against
they check against neon.
Right.
And
yeah.
the other thing is, again, it would be impossible from the laws of thermodynamics to have such a tracking of heat and helium-4.
If I understand correctly, we're saying if, in fact, you're giving up mass, you're generating energy, and the byproducts are helium.
Right.
And that's important. If you've got a lot of helium, that's part of the proof that it's a nuclear reaction.
Absolutely.
And it is the proof. And what people have, the mindset of thinking of things at high temperature has been that you have to get these high energy particles. But you don't. That's just a residual effect associated with what happens in free space and when you collide things at a point. You don't, for example, get the same high energy byproducts if you change around the nuclei a little bit, so that if you have a triton, or if you have helium-3 colliding with a deuteron, you can get the helium-4 directly. You know, I mean, in other words,
you get a high energy particle.
You get a high energy particle, yes, but it's not exactly. But the helium-4, you don't get a gamma ray then. You know, and so the rules about the gamma rays are not sacrosanct at all, and it really gets down to the higher order processes associated with you know, the need to conserve energy and momentum.
Let me show you. This is the first excess heat data that was published by Arata and Zahn. Did we show this picture?
Yeah, you were in Japan, and were these the people?
These two people here. That's Professor Arata and Dr.
He's with
Zahn.
the white hair. Yes.
Right. He's the one.
There looks like
retired.
1, 2, 3, 4, 5 people around a table, and
Well,
we'll be able to get you
This is when we were giving
a close-up of this.
Yeah, I was talking about what I'd presented at the ICCF6 meeting in Hokkaido.
That's the sixth international conference on cold fusion.
They're solid-state physicists.
And this
these
must
are
be
the people, just the two of them, work in the laboratory for 7 years in a very dedicated way, and they've built up beautiful equipment and gradually learned how to work with it.
Is this a picture of the type of equipment they're using?
Well, this is the excess heat part. It's not. This is relatively simple compared to the part used in preparing the materials that go into this and analyzing the gases. But these are two cold fusion cells in stainless steel thermos bottles, and the heat is measured by flowing cooling water in there and measuring how much it rises in temperature and how much cooling water is flows through that. Very simple process. And the input power is just measured by volts times amps.
Yeah, it's a very simple. It's basically a very simple technology. Part of the problems that Pons and Fleischmann faced were because it was such a controversial thing that they were raising, that their calorimetry was questioned. This is, you know, impeccable calorimetry. You're just flowing water around something and seeing how the temperature changes. It's obvious.
Easy.
It's 19th century. There's no
rocket science here.
Doesn't
really take a rocket scientist to figure this out. Although some people will well.
All you need to know is 1 calorie raises 1 cubic centimeter of water, 1 degree centigrade.
Yeah. Well, and now the other thing about this, though, that's very important, that gets back to something that we find amazing, is that one of the reasons, there's good reason to believe that one of the reasons that they have been very successful, they've been successful 6 out of 6 times with their electrodes. And a key point here seems to be very much something that is near and dear to our hearts, which is the materials aspect of it. These people work with a very specific form of material, very different than what was in the initial Pons-Fleischmann apparatus. It's different simply because there are 2 things about it. It's smaller. It's significantly smaller.
Very small crystals.
Very small crystals, and it actually happens to be at the size that we suggested would be the optimal size, which is about 1 billion unit cells. For a characteristic dimension of about 1/2 micron. Now, the other thing that is important is that they are able to get these crystals every time. They have a device set up so that they have the powder in a particular configuration, and they put the heavy water, they electrolyze it, and they get D+ going through these this powder, and they build up gas on top, a D2 gas, and the D2 gas pushes down on the powder and gets it to this small size, and when it turns on just at this sort of magical size.
Let me just show you one thing. I know this is a small graph, but that's
It looks like it's on number 7 up the upper left-hand corner. It shows some lines zig and zagging up in a square box.
And this dotted line here is the voltage times amps of electrical power in, and this is the heat coming out.
That's the upper line.
The upper line.
And the very lower line is the power?
Power going in.
Okay.
So this powder is encapsulated in a palladium bottle, and as Scott says, for the first 2 weeks, this is 2 weeks roughly from A to B.
Yeah, you don't get anything.
The pressure is building up inside the bottle, and you don't get anything. But once the pressure reaches a certain point, and you continue your electrolysis, then you get all this excess heat. And this is something like 80 watts lasting for 2 weeks, which is just much more compared to what the Fleischmann and Pons people were getting.
You say the secret is in the cathode metal, the way they're packing it, the way the crystalline structure.
Right. Exactly.
Are they the leading edge of technology in the whole world, do you think?
Well, absolutely.
Are you studying everything that's going on?
Part of the problem has been in the materials. The New Hydrogen Energy Program has a big program. 5-year program, $30 million from the government, from the Ministry of Trade and Industry in Japan. And at this conference that Talbot and I both went to, the big message from them was, we can't get it to work. Or we got it to work once. You know, and part of their problem has been the materials part of it. And they've been taking an in quotes cookbook recipe that was put out by people from SRI International. And these people at SRI International have done a great job, but they have all along said, quite correctly, that it works on some batches of material and others it doesn't. Now, the thing that is unique about this stuff is that they're getting the same crystals.
But there is also the other group, which we don't know, I don't know as much about, which is Ghazi's group, which is also seems to. They're working with.
They got large amounts of heat too.
They also are working with small crystals because they're working with very fine wires.
Ah, I hadn't remembered that.
Yeah,
that's
very fine
true.
wires, and so they may also be on the cutting edge. In fact, I'm sure they are.
I think
so.
They
these
are.
Two groups, Arata and Zhang and Ghazi's group at Rome, are certainly providing the leadership.
But
right
now
where's America? Where's our country?
Well, that's a good question.
Well, you know, there's another interesting point about this, though. And it does harken back to the early days of, I happen to know the Naval Research Laboratory rather well, and it harkens back to that. One thing that they did was they started paying attention to what is happening in the materials. They did pay attention to it. There are funny things when you do this. There are funny things that can happen. They are complicated experiments. The one thing that they found that was very, very provocative was that they were finding redistributions, what looked like redistributions of isotopes as a result of, doing this electrolysis. Now, I'm not saying that those experiments were right or wrong, but the thing that we can really bring to the forefront is at places like Los Alamos, at the Naval Research Laboratory, at Lawrence Livermore. They can bring the materials expertise. They can really bring it to the forefront. We have that technology.
But we don't have they don't have supported programs.
That's
in
right.
This area.
And that's what's needed. The government has got to relook at it from the viewpoint of solid-state physics instead of looking at it with what I call blinders, and they were justifiable blinders at the time, of hot fusion.
But
okay.
Okay.
Well, just one thing. We at Oakton International feel that there should not only be a government program that works on these Arata Zhang techniques, but also there should be a program in private industry.
Absolutely.